Which ये मैं कहाँ रुको क्या? नहीं उसको मत छोड़ो, ये उसको मत छोड़ो। हाँ, ये उसका छोड़ो, चलो उसको छोड़ो, उसका है ना वो। नहीं नहीं, सुनिए सुनिए सुनिए। नहीं नहीं, ऐसे मत करो, ये रह नहीं रखो इधर। Oh, is it on? No, I think it's not reflected. So, good evening, everyone. Thank you for joining us for the inaugural MS Vardya Memorial Lecture, which will be delivered by Professor Erwine Vandishaw. So we are ready to begin. But before we start, may I kindly ask the audience members to switch off the mobile phones, your mobile phones, and or set them on silent mode or airplane mode. Thank you. Thank you for your cooperation. I now invite the director TIFR, Professor Jairam Changalur, to welcome the speaker and audience to TIFR and share a few words about the institute. Jairam.
Thank you, Manoj. And I'm delighted to welcome all of you to TIFR. As you probably are aware, research at TIFR covers a very large range of topics, everything from what happens in the very distant cosmos to, much more nearby things such as the development and, understanding the development and the functioning of the human brain are activities that we undertake at TIFR. In many of these areas, the kind of research that we do, we are often the only place in the country where this research happens. So as such, we regard it as part of our mission to try and communicate to the public at large, what it is like, what the excitement of doing cutting edge science is like. So part of this we achieved through having a very active outreach program. As TIFR is spread over many cities, our outreach program is also spread over the country. For example, at Kodad village, which is near Pune, where we have TIFR's giant meter wave radio telescope, we run what is probably the largest science day program in the country. Here in Mumbai, we have Chai and Why, a series of public talks, which has run continuously on Sundays for more than a decade at the Prithvi Theatre in Juhu and also at Ruparel College. And of course, we have a long, long tradition of having public talks in this auditorium, the Homi Bhabha Auditorium. So for those of you who'd like to keep up with this, I'd encourage you to look up our webpage and to follow our social feeds for the schedule of upcoming events. As we heard, the talk that we have today marks the beginning of a new series of these public talks, the MS Vardya Memorial Lecture Series. Although the series is new, as I said, it is part of TIFR's long tradition of engaging with the public and trying to communicate to the public cutting edge science. I'm extremely grateful to Rekha Koita and the family for providing the generous endowment through which this program has been funded. We are also very fortunate to have with us a very distinguished speaker, Professor Erwine Vandishaw, to give the inaugural lecture of this series. And the topic that she has chosen, I know, will be of great interest to many of you all. You'll shortly hear a more formal introduction of the speaker, but I would like to take this opportunity to thank her for accepting our invitation and coming here for this visit. In addition to the talk today, she also gave a seminar at the department yesterday and is also spending some time at TIFR interacting with the faculty at the astronomy department. Thank you, Professor Vandishaw, for making the time for this. I would also like to take the opportunity to thank Mrs. Koita for this very generous gift, without which none of this would have been possible. This kind of philanthropic support is important not just in carrying our mission forward, but also in allowing us to expand out in directions which are interesting, which are exciting, but which are otherwise difficult for us to explore. So thank you again. With that, I stop. Welcome again to TIFR.
Thank you, Jairam. May I now invite the chairperson of the Department of Astronomy and Astrophysics, Professor Baswati Mukherjee, to say a few words.
Professor Chengalu, Professor Dishoeck, Mrs. Rekha Koeta, Mrs. Shobha Vardya, colleagues, students, and members of the audience. On behalf of the Department of Astronomy and Astrophysics, it is my pleasure and privilege to welcome you all to the first MS Vardya Memorial Public Lecture. This lecture series has been instituted in the fond memory of Professor MS Vardya, who together with Professor SM Chitre established the Theoretical Astrophysics Group in TIFR in 1963 and was a faculty member at TIFR till 1993. I express my deep gratitude to Mrs. Rekha Koeta, daughter of Professor Vardya, for this generous endowment, which has made the lecture series possible, and to Professor Erwine Van Dishoeck, eminent astrophysicist, for accepting our invitation to deliver this lecture. We thank Mrs. Vardya and the members of the family for being here today with us. Professor M.S. Vardya started his research career after an MSc from Benares Hindu University when he went for a PhD at Yale University, where he worked on the envelopes and interiors of late-type stars. The main emphasis of the thesis was to compute hydrogen-helium adiabates, incorporating the physics of molecular hydrogen to provide better boundary conditions to radiative cores in late-type stars. He subsequently did postdoctoral work in Berkeley before he joined TIFR as a faculty member. His research work primarily involved development of model stellar atmospheres for late-type stars, including opacity effects arising due to the presence of molecules and molecular ions, and later he also looked into data from observations. He was a pioneering molecular astrophysicist whose work probably has become more relevant in the later years as observations of molecules in astrophysical environments became possible with improved technology. He, together with his student, Professor S.P. Tarafdar, organized one of the first conferences in astrochemistry, IAU Symposium 120 in Goa in 1985, almost 40 years now. The summary of the proceedings of which said the symposium covered almost all aspects of astrochemistry, from the early universe to comets and meteorites. Basic atomic and molecular physics, experimental and observational results, and theoretical calculations and modeling all were stressed. For those of us who are in the field, we know how immense these things are now and how important they are will become more evident from Professor Van Dishoeck's talk. Professor Vardya had a long stint also as the editor of the Bulletin of the Astronomical Society of India during 1966 to 1973. Having Professor Van Dishoeck, a very eminent molecular astrophysicist, as the speaker of the first MS Vardya Memorial Lecture is not only our privilege, but also a befitting tribute to the life and legacy of Professor MS Vardya. I welcome you all to this lecture and thank you all for being here.
Thank you, Baswati. May I now invite Ms. Rekha Koeta to share a few words with us?
I am a very warm welcome and thank you to everyone who has come here to attend this lecture. I'm actually, just kind of swept away by several waves of nostalgia as I walked into Homi Bhabha Auditorium today after so many years, because, being like a TIFR child in a sense, right? We spent several moments over here. We have attended so many events, right from the TIFR Founders Day to cultural events to a lot of lectures and other, such series talks such as this one. So I think this entire space played a big role in enriching our lives, which we didn't realize, as children, but I understood the value many years later. And I'm hoping that, and I'm sure rather that, lecture series such as this one and, the continuing tradition of TIFR will continue to do that for, several other people around. So, I mean, before I begin, a big thank you to, Professor Chingalur and Professor Bhaswati for helping me to put it together. And of course, my friend, Arnab Bhattacharya, who's my batchmate and who was the first person I reached out to when I wanted to set this up. So, my father was, as Professor Bhaswati mentioned, he spent several years at Berkeley before coming to TIFR. And one of his kind of goals was to really develop and, expand on research in India in the field of astronomy and astrophysics, which is why he kind of wanted to come back. And together with Professor Chitre, or Chitre Uncle, as I've always called him, started this department, which was at that time known as theoretical astrophysics. And all his life, I think he's, like many others in TIFR, right, life was always dedicated to their topic of research, a simple life dedicated to science. And that's what I kind of have seen. I think there was always this thirst for knowledge and learning. And, I think one of the things which really made him happy was just even popularizing, science and the whole knowledge of astronomy and astrophysics. And he was always very encouraging of youth wanting to get into this field. So when I thought that, I wanted to do something at TIFR in his memory, and when, while discussing with Professor Bhaswati, she, gave me this option of a lecture series in his name. I kind of really jumped at it. And I'm really grateful that, we're having this first inaugural lecture today, and even more grateful that we have someone as accomplished and distinguished as, Professor Van Dishoeck to come and deliver this lecture. Because, I mean, not only, of course, she's very accomplished in her research and very well known, but she's someone who also has, interacted and known my father. And her area of, research is very closely related to his areas of interest in astrochemistry and astrophysics. So really big thank you for you to come all the way here to India and deliver this lecture. So again, just once again, thank you to everyone for coming. Thank you to the entire team at TFR for organizing this. And, I look forward to this lecture and to many more to come in the years. Thank you.
Thank you, Rekha. Before I cede the floor to our distinguished speaker today, I want to provide a brief bio of Professor Van Dishoeck for those of you who may not be familiar with her work. Professor Erwine Van Dishoeck is a professor of molecular astrophysics at the Leiden University, Netherlands. Her primary research interests are in the broad areas of astrochemistry and interstellar molecules, a research area that was close to Professor Vardya's heart. Professor Van Dishoeck and her group innovatively combines the world of chemistry with that of physics and astronomy to study the molecular trail from star-forming clouds to planet-forming disks. They follow the physical and chemical evolution during star and planet formation and beyond. In addition, she also leads a laboratory astrophysics group at the Leiden University. Now, a brief description of her career trajectory. Professor Van Dishoeck obtained a PhD degree in 1984 from Leiden University, jointly working with Professor Habing at Leiden and Professor Alex Delgarno at Harvard. Her thesis work was on photodissociation and excitation of interstellar molecules. She then, after her PhD, she moved to Harvard for her postdoctoral research, where she was a junior fellow of the Harvard Society Fellows from 1984 to 87. During this time, she was also a visiting member at the Institute of Advanced Studies, Princeton. She was also an NSF visiting professor at Princeton University from 1988 to 87. After her postdoctoral stint, she took up a position as an associate professor at cosmochemistry at the Department of Geology and Planetary Sciences at California Institute of Technology. And she spent 2 years there. And in 1990, she returned to Leiden as senior lecturer, which is equivalent to associate professor here. She became the professor of molecular astrophysics at Leiden in 1995. She has a distinguished academic career and has published over 630 refereed papers, more than 50 invited reviews, which have collectively garnered 44,000 citations and an H-index of over 100. She has supervised and co-supervised over 50 PhD students and more than 30 postdocs. Some of them have gone on to become leaders in their field. To mention a few names that might be familiar to people working in astronomy and astrophysics: Klaus Pontoppidan, Greg Herzog, Ninke Vandenmarel, Lars Christensen, Benoit Tabon, a few names that come to mind. She has been a member of various academies around the world: the Royal Dutch Academy of Sciences, US National Academy of Sciences, American Academy of Arts and Sciences, Royal Astronomy Society of UK, to name a few. In addition, she was also part of several science policy committees. Professor van Dishoeck has been the president of the International Astronomical Union for 3 years, from 2018 to 2021. She is currently a member of the Board of Trustees of the Institute of Advanced Studies, Princeton, and the scientific director of NOVA, the Netherlands Astronomy Research School. She has also been member of various committees that proposed and supported many of the big astronomical facilities in the last 2 decades, namely the Herschel Space Telescope, the Atacama Large Millimeter Array, and the James Webb Space Telescope. She has been a member and a chair of ALMA Science Advisory Committee and ALMA Board. She is the co-PI of the European JWS MURI Consortium. She has been a recipient of several awards for her scientific contributions, mentoring, and advisory role that she has played in the advancement of astronomy and astrophysics around the world. She has been honored, prominent among these awards are the Kavli Prize for Astrophysics in 2018, James Craig Watson Medal of the US National Academy of Science in 2018, the Karl Schwarzschild Medal of the German Astrophysical Society in 2019, and the Prix Jules Janssen of the French Astronomical Society in 2020. Please join me in welcoming Professor van Dishoeck to deliver the inaugural MS Vardya lecture.
I think it's on. Yes. Okay, good afternoon, everybody. Members of the Vardya family, director, chairperson, colleagues and friends, students, postdocs, everybody who is listening online on YouTube. It's fantastic to be here today. It's a huge honor for me to be the first lecturer here of this new series. And it's really wonderful to be here with you and to share these few days with you and to hear all about also your exciting research that you are doing. So today, I will take you actually to space. I will take you to the space between the stars that you see so beautifully on this image. And we are going to see how stars and planets and maybe even the ingredients for life in space are being made there. But before I do that, let me just go here. I want to pay tribute indeed to Professor Vardya, who I had the pleasure actually of meeting in 1985. I'll come to that in a moment. Professor Vardya was indeed a pioneer actually in astrochemistry. I think now we realize that he was actually way ahead of his time because one of his topics was to study the very low mass stars and the atmospheres of these very low mass stars and the various molecules that are in there. And he had an article in the very prestigious Annual Reviews of Astronomy and Astrophysics on that topic already in 1970. He did some of that research. This is his most cited paper in 1966. Not only in the US, but actually in my home country, in the Netherlands. As you see over here in the acknowledgement of that particular paper, he was in Amsterdam and then also in Utrecht in Zonneberg. And he is grateful here to the various foundations that supported him actually during that visit. So it's a real pleasure to realize that some of this work that he did actually had much of his roots and also inspirations when he was actually in my home country in the Netherlands. So 1985, let's go back to 1985, because that was actually a very important year for astronomy and for India especially, because that was the year of the General Assembly. The only once every 3 years that our community, the worldwide community of astronomers in all fields, actually get together. And that was in 1985 in New Delhi. It was held in November. And you see that actually this is the invitation for the opening ceremony that I still have, where actually Rajiv Gandhi was actually the speaker at that time. So it was a very high level meeting. After that meeting, actually with 25 astrochemists, we actually went from New Delhi all the way down with 5 stops, seeing much of India along the way, to first Mumbai and then to Goa. This is the beautiful resort just south of here, where the first symposium actually on astrochemistry was held, IAU symposium number 120. And so here you see actually the group photo there. Here's the chairperson, Delgarno. Professor Vardya is in this picture, but interestingly, he's very modestly somewhere here in the back. So there's maybe that's a sort of a little bit of characteristic of him, that he was very prominent scientifically, but maybe a little bit modest when it came to these kinds of events. He was, of course, the editor, the main editor of the symposium book on astrochemistry, which I actually have here. This is the one from the library. I still have it in my own library as well, because it was really setting the scene for much of our field. Good. So that was 1985, and now we fast forward by 40 years. And as we will see, even though the ingredients of what was discussed at that symposium are still the same in astrochemistry, going all the way from the early universe, from galaxies, from star-forming clouds to our own solar system to comets, that has not changed, but we have gained tremendously in terms of observational capabilities and our knowledge of all of these systems. And during this talk, I hope to give you a little bit of a flavor of that. It's a talk that is aimed at a general audience, so I will not go into many detailed specifics, but I hope that you'll get at least a taste of what has been happening in this field over the last decades. So first, viewing the night sky is something that is available to everybody everywhere in the world. That's the wonderful part of it. And just recently we had the excitement of another comet that could be seen actually with the naked eye. You see here comet 2023 A3, here above Chile, but also here above Tucson. And I hope that some of you also got to see it here in India. And whenever you look at the night sky, you cannot help to wonder. You cannot help to wonder, where do we actually come from? And what is our place in this gigantic universe? And as we will see, these tiny, relatively small objects like comets actually play a very important role in that. They are the building blocks for new planets. And they are actually full of molecules. They are really an chemistry very rich. Now, one of my own hobbies is actually astronomy and art. And so while walking actually in the building, astronomy building, it's a delight for me to see all that beautiful art hanging there. Now, as a Dutch person, I don't have to go very far in terms of astronomy and art. Of course, Vincent van Gogh just had to paint the starry night, and he's done that many times. And this is just one rendition of it. And you see here beautifully the Big Dipper over the River Seine. He painted this one in Paris, actually. But you see this fascination of artists with the night sky. You see that throughout the entire world. If you go to Australia, then the indigenous people have these dreamings. And one of their very important dreamings is the Milky Way dreaming. That's sort of part of their way of living, their cosmology that they have. And you see here a very nice example of this, where you see the Milky Way, but then also the Seven Sisters actually in the heart, and with at the heart of the Milky Way, and the Orion actually chasing them. But we can also go to India, and we also find examples there of how the night sky has inspired actually various different paintings. This is just one example, but here are a few other examples, and especially this petroglyph over here, which is many thousands of years old, and maybe depicting actually a supernova that went off already in that time. Good. So the night sky tells us about the stars, it tells us about the planets, but few people actually think about what is actually in between the stars. So the regions in between the stars are not empty, but they are filled with a very, very dilute gas. And in addition to that gas, there are also small solid particles, and they make the clouds look dark, actually, like you see here on the Milky Way. And so the story I'm going to tell you today is that our origins, the origins of solar systems like our own, actually stem from one of these clouds that you see over here. If we were able to go out of our Milky Way and look down on it, and that's what you see here in an artist's rendition, although it's based on actual astronomical data, then we would see here the center of our galaxy that we now know contains a supermassive black hole. But it also contains these more than 250 billions of stars. And our sun is just one of these many different stars that is a rather ordinary star, and somewhere halfway in the outskirts of our galaxy. And so we live on a actually rather tiny planet, a small rocky planet, around that star, a rather ordinary star somewhere in the outskirts of our galaxy. So the whole question as to whether we are unique, because our galaxy is just one of hundreds of billions of galaxies in the universe, takes on a different meaning when you realize just how many possibilities there are for having solar systems elsewhere. Now, even though there have been speculations about planets around other stars than our sun, so-called exoplanets, even though they have been around for centuries, the real scientific proof didn't come until 1995 with the discovery of the first exoplanets that led to the Nobel Prize in 2019. And there are various techniques to do so. One of them is to look at the transit of a planet in front of a parent star when you see a little dip actually in the light curve. But the detection of, and we know many of these exoplanets, has undoubtedly triggered sort of very fundamental questions, not only what are these planets like, but also how were they formed? How unique is our solar system? And which of these planets could actually be habitable? We now know that these planets come in all different kinds of forms. Some of them are very small, like our Earth. Some of them are very big, like Jupiter or Saturn. But it actually turns out that the bulk of these exoplanets are of a type that we do not have in our own solar system. Most of them are so-called super Earths, a few times the mass of the Earth, or mini Neptunes, a little bit smaller than Neptune, which is 10 times the mass of the Earth. And so we know that on average, every star has a planet. So planets may actually be more common in our Milky Way than stars. And now that we know that they are there, the next step in this research is undoubtedly studying their composition and studying whether they could be habitable. And this is also very closely linked to how we, our solar system, were actually formed some 4.5 billion years ago. And we have some clues about that, and they were actually discussed already in that particular symposium. So we get information from meteorites. And they originate from parent bodies, asteroids, and there have been exciting missions recently, OSIRIS-REx and Hayabusa, to asteroids and picking up a little bit of material and bringing it back to Earth to study the composition and what may have affected the material in the inner solar system. The outer solar system, we have our comets. Comets are not just rock, but they are a mix of rock and ice. And they have been far out in the solar system, so they have been a little bit in a deep freeze. Very little change since the birth of our solar system. And about a decade ago, the Rosetta mission from the European Space Agency actually landed on a comet for the first time and sniffed the gases that came out of that comet and gave us an impression of sort of the material, the building blocks that were available at the start of our solar system. So both of these are also messages from our early solar system that we can now start to connect with other solar systems that we find. So let's start our journey actually to study these formation of these stars and planets. But first I want to pay tribute to the many students and postdocs and colleagues that I've had the pleasure to work with. This is just a small collection of the wonderful people that I've been able to work with. And much of what I'm going to tell about here is really to their credit. Okay. You undoubtedly recognize this particular constellation here, Orion. And as I mentioned already, rather than looking at the stars themselves, what we are interested in is the emptiness between the stars. The very, very dilute gas that is actually in between the stars. And some of that dilute gas can actually be in more denser concentrations. When they are in somewhat denser concentrations, we call them clouds. And that is, for example, the Orion clouds, the Orion molecular cloud, and Orion nebula that you see over here. Now, the darker parts, the denser and darker parts of these clouds, that is actually where we find the molecules, and that's also where stars and planets are being born. So just to give you an impression, the densities in these clouds is about some 10,000 particles per cubic centimeter. To compare that, 1 cubic centimeter here in this room contains some 10 to the 19 particles per cubic centimeter. And even a good ultra-high vacuum in one of your laboratories here on campus usually contains still of the order of some 100 million particles per cubic centimeter. So these clouds are really much, much emptier than anything that we have normally here on Earth. They're also very cold. They're only a few degrees above the absolute zero. Again, if you want to think about it on the Celsius scales, it's minus 260 degrees. Now, they are so dark because they contain not just gas, but also these tiny little dust particles. So think about them as sand that you have on the beach, only about a factor of 1,000 smaller. And these small particles, just like smoke, actually absorb and scatter the radiation. And that is what makes these clouds look dark. I think if you have a lot of smoke in the atmosphere, you also know that you cannot look actually very far. So the good thing is that that then shields molecules that are actually inside these clouds from the dissociating radiation that is present from the nearby stars. So that is why these dark clouds are such important sites. Now, the astronomer's periodic table looks a little bit different from what you're used to in high school. Hydrogen is still the most dominant one here. If you put that as 1 by number, then helium is at a level of about 10% by number. But you also know that as a noble gas, helium doesn't do much chemically. So the real interesting chemical elements like carbon, nitrogen, and oxygen are way down at a fraction of a promille, actually, with respect to hydrogen. So, you know, chemists would tell the astronomers still in the 1960s that don't even bother to look for molecules in space. You won't find them because it's so cold, it's so tenuous, they will actually, the atoms will not be able to find each other. Now, fortunately, the astronomers didn't listen, and they started to tune their receivers on their telescopes, and they found one molecule after another, starting in the 1970s. And then since also this symposium, we have had the fortune of having fantastic facilities actually being developed over the past 40 years that are particularly well suited for studying astrochemistry and molecules. And that is because we are able to go to the longer wavelengths, so not just looking at light that we see with our own eyes, but optical radiation, but also going to the longer wavelengths, the infrared and the millimeter wavelengths. And it was already mentioned, the Herschel Space Observatory is fantastic. Of course, the Atacama Large Millimeter Array. We also have here close by, actually, the GMRT in India is also a very powerful radio telescope, which can observe some molecules. But then we also have the future, JWST, being launched. I'll say more about that, producing data since 2022. And then the future is the extremely large telescopes that are being built and that will also have infrared capabilities. And here you see one example of the European ELT that is already quite far in terms of their construction. So this is to say to the younger people that there's a real good future for you with the ELTs coming online and starting to produce fantastic data by the end of this decade. Now we know that these interstellar clouds have a very rich chemistry. More than 300 different molecules have been found. Just to give you a little bit of taste, it's simple molecules like water, and we can uniquely identify them by their fingerprints, thanks to the laws of quantum mechanics. Every molecule has its own unique fingerprint with which we can identify them. Here you see a fingerprint of water, but then there are also other molecules. Here you see dimethyl ether, methanol, various other molecules that have actually been detected. One interesting molecule that has been detected and that is actually quite abundant is not just methanol, but actually also ethanol. If you think of the Orion molecular cloud, and probably that cloud by itself contains some 10 to the 27 bottles of whiskey that you can do that. But you have to tap it, so you have to go there, and it may not be 40%, but it may be only 1% with respect to water that you have there. So how do we observe these molecules? Well, a molecule can both rotate. That's what you see over here. That's one of the molecules in the gas phase. It can also vibrate. It can doing stretching motions, and it can also do bending motions. That is both gas and also in the ice. And with those kinds of diagnostics, we have been able to find not just these molecules that we see over here, but even more prominent molecules like the so-called polycyclic aromatic hydrocarbons that are also present in the exhaust of your cars. But not yet the first amino acid, the simplest amino acids. Neither this particular molecule, which you may not recognize, that's actually caffeine, may not be important for the origin of life, but it definitely plays a large role in the maintenance of life here on Earth. So in addition to the gas, we also have ices. These little dust grains are so cold that they act as a deep freeze. So just if on a cold night, well, I don't think you have those cold nights here in Mumbai, but maybe if you go closer to the Himalayas, your molecules actually will freeze out on your windshield and form an icy layer. That's also what we have here in space. These small sand grains actually act as a deep freeze on which various atoms, molecules can freeze out. And once they are frozen out, you can have reactions that normally don't occur in the gas phase. So oxygen is actually hydrogenated to water, carbon to CH4, nitrogen to ammonia, and carbon monoxide, which is very abundant in space, can be hydrogenated with 4 hydrogens to make methanol. So that's the simplest alcohol. So we can now also say that actually the alcohol is literally on the rocks in space. And also we have some CO2. So that provides actually the bubbles that we have in our cocktail. Good. So what we actually try to do is not only observe these molecules, but we also try to understand how they are formed. And for that, we have the Leiden Laboratory for Astrophysics, of which I was the director for a number of years. Then it was taken over by Harold Linnaerts, who unfortunately passed away just last year. But it has been a wonderful facility actually to simulate these conditions in interstellar space. We can simulate low temperatures. Of course, we cannot simulate the very low densities. That is also what we don't want, because then a reaction would take 10,000 years to occur. So we want to speed it up a little bit so that our students can do their experiments in 1 year. In one day, and in that way understand what is happening actually in space. And one of our focus has been on water, and especially we now know through a combination of observations and laboratory experiments and theoretical simulations that most of the water is actually formed on the surfaces of these tiny dust grains. So here you have once a day a hydrogen atom lands. It moves around on the grain, it finds another hydrogen, makes molecular hydrogen, but it also can find an oxygen, the red balls. You can even make molecular oxygen. Now we're making actually hydrogen peroxide. All these intermediates we have also observed in space, and now we make 2 water molecules. And now we're going to speed up from a few days to 10,000 years. And now we make lots and lots of water molecules, and these will form then an icy layer around this dust grain. So we think actually that this is the way in which most of the water that we have here on Earth, that you have here in the ocean, that you have in your body, is actually made. That it's made already in these cold, dark clouds actually before they collapse to form a new star. And as one of my colleagues put it, if you think about it in that way, water is actually older than the sun itself. So think about that. If you take a sip of water, as I'm doing now, that those water molecules were formed already some 4.5 billion years ago. Of course, they have sublimated and recondensed again, but the bond between the hydrogen and oxygen actually originates from that time. Good. So we have been observing water, and especially the Herschel Space Observatory, which was above the Earth's atmosphere, was very good at observing water. And from the strength here of this signal, we can calculate how many water molecules there are. And that translates into a useful unit of oceans that were in this particular disk around a young star, planet-forming disk. There were some 6,000 oceans of water available for building planets. So plenty of water actually available to make new solar systems. So this work has not gone unnoticed. Actually, the Big Bang Theory at some stage got interested into water, and even the ionized water that was being detected with Herschel, and they put it on their screen. So to summarize this part, interstellar clouds actually have a surprisingly rich chemistry in spite of the fact that they are so tenuous. We see water. We see complex organic molecules around nearly every forming star throughout the Milky Way and even beyond in also other galaxies. And there's a large similarity actually in the composition if we compare it quantitatively with comets. So the first conclusion is that the building blocks actually for prebiotic material are very widespread throughout the Milky Way. So let's now go from chemistry to a little bit of physics. So how is a new planetary system actually being born? So here we have one of those dark clouds, and for a long time, say millions of years, it can be stable, but eventually gravity wins. And that means it will simply start to collapse under its own weight, and it will form a young star. But because there's a little bit of angular momentum associated with the motions, that means that material cannot continue to fall in radially, but a fraction of the material will end up in a disk actually around the young star. And it is that disk that is so important for building actually the new planets. And so what you see here is actually an animation of one of these planet-forming disks, where even though we usually don't see the planets themselves, we see their result that they have on this disk because of the gap that they actually introduce in this disk. So this theory of planets forming in rotating disks of gas and dust, of course, dates back again many centuries. There were speculations already by Kant and by Sonneborg, the solar nebula hypothesis, because all of the planets in our solar system also rotate in the same direction in one plane. But again, the firm scientific proof didn't come until 1996, when finally these disks were actually detected and observed. Now with ALMA, we actually find these beautiful images of planet-forming disks. This is a very famous one that was made where we see not a very smooth disk, but we see actually these structures in these disks that are indicative of planet formation in action. And in fact, here's a nice collection that was made where there's a whole gallery where you see all kinds of structures, not just cavities and gaps, but also asymmetric structures and even spiral structures that are all indicative of planets that are actively forming in these disks. So to summarize some of this part, nearly all young stars are surrounded by disks with sizes actually comparable to those of our own solar system, with masses that are enough in most cases to form planets, maybe not always giant planets, but sometimes terrestrial planets. And then there are structures in these disks that points to planet formation in action happening at this moment. And again, nearly every young star is surrounded by such a disk, so the ingredients for planet formation are also common in our Milky Way. So a couple of words about astronomy and technology, also because I know that TIFR actually has a large instrumentation group as well, and I had the pleasure of visiting the labs actually this afternoon. Because astronomy is actually driven forward by new technology. Well, what was the problem here? Well, we wanted to observe these disks here in an artist impression, but they were so small. They were tiny. On this particular slide, they would be like, a little pinprick there. You can hardly see them. So we needed to develop new technologies, new instrumentation in order to detect them. And one of those is indeed the Atacama Large Millimeter Array, the first worldwide collaboration in astronomy between Europe, North America, and East Asia. And also Indian astronomers are making good use of the ALMA data. It's a fantastic facilities. So here you see how such an array works, that all the telescopes at the same time actually follow an object on the sky, and then their signals are being combined in a giant computer-designed correlator where they are then used to simulate an image of a telescope that would be kilometers in diameter and therefore seem much sharper than that any single dish would be able to do. Good. Well, the other new kid on the block is, of course, the James Webb Space Telescope. At this moment, when the launch on 2021, when this final stage of the Ariane rocket and JWST was released, that was a very emotional moment. There you see actually the solar panel coming out. That was sort of bye-bye Webb. That was the last that we were able to see of Webb when it disappeared and went on its way to where it is at the moment. So this is really the tributes to the thousands, even tens of thousands of engineers and technicians and managers that worked on this project in order to make it happen. And so since it is playing such an important role now in these days in astronomy in the last few years, let's follow a little bit more of the excitement of Webb and some of the building of Webb. So my own involvement actually dates back more than 25 years when I was a member of the scientific advisory committees of both ESA and NASA on the type of instruments that should be on board of Webb And then we pushed actually to have a mid-infrared instrument on board, and that was accepted. And then we spent a good 10 plus years building it actually. And some of the spectrometer main optics were actually built in the Netherlands, and you see some of that over here. So what happened then is after it was built, then our Dutch part, just to give you an impression, that actually all happened between 2002 and 2008. Then it was delivered to the UK, there it was integrated, and then it was tested on the ground. Then it was shipped already to Goddard in 2012. And then integrated into where the box where all of the instruments are from Webb. There you see our Miri sitting there on the side. Then, of course, the whole telescope also had to be built. Here you see at Goddard some of the images of the golden eye that was being built there. The instruments that were being put at the back of the telescope. Then once that was done at Goddard, it went to Houston, where there is actually, they used the facility that was still available from the Apollo era. This was the test chamber for some of the Apollo missions, of the instrumentation there, and that was sort of rebuilt because nowhere else there was such a large cryogenic facility there where JWST could be tested completely end-to-end with both the instruments and also the optics. Then from Houston, it went to Los Angeles. That's actually where the sun shield was installed. The sun shield, which we'll see, is crucial to keep the telescope cold. That was another whole development, and not everything did go well there. So that resulted in another delay of a few years. Of course, COVID also didn't help. But then in late 2020, it was actually shipped from JWST through the Panama Canal to French Guiana, where the Kourou is, where the launch site is, where actually the European Space Agency, the Ariane 5 rocket actually was the launcher. Now, JWST is 6.5 meters, but the largest cone of a rocket is only 4 meters. So JWST had to be folded a little bit like an origami. It had to be folded here in the nose of the rocket, and that was quite a feat. So then it was put here in the top, and then it had to unfold in space after it was launched in 2021. Now, miraculously, everything went okay. So there were something like 300 points of failure, and none of them materialized. And JWST actually traveled past the moon, so it's about 1.2 million kilometers, about 4 times the distance of the moon. That's where the so-called Lagrangian point is, where the gravity of the sun and the Earth are actually compensating each other, and it's a very stable point. And there it travels actually with the sun, with the Earth around the sun. But it has to have this sun shield always in the direction of the sun and the Earth and the moon, because JWST looks at heat radiation, infrared, that's heat radiation. And so everything that emits heat is actually causing noise. So to prevent the noise, you have to keep the telescope cold. And that is why we have that sun shield that is always directed in the direction to keep out the radiation from the sun and the Earth and the moon. So what makes Webb actually unique? Well, Webb is big, 6.5 meters. You see it here in a 1-to-1 scale model, much larger than the Hubble telescope. Also, the eyes of Webb are unique. It looks actually in the infrared part of the spectrum. So this is the part of the visible that we see with our own eyes. You're all familiar with radio. You're all familiar with X-rays. The infrared is somewhat longer here than what we see with our own eyes. And a lot of that radiation is actually blocked by the Earth's atmosphere, which is why we need to go to space in order to see it. Why otherwise do we go to the infrared? Well, that's also to be able to penetrate dust clouds. because we want to actually go and look inside these dark clouds, because that is where we can see the forming stars and planets. And we can only do that at the longer wavelengths. So there are actually 4 instruments on web. There are cameras, like you can have with your iPhone. There are also spectrometers that basically dissect the radiation into the colors of the rainbow. And there are actually very sophisticated spectrometers. They don't just look at one point, but they get actually spectroscopy on many different sources at the same time, either closely related or in what we call an integral field unit, where we basically make a spectral image of a source. So the MIRI, this is the instrument that makes many of the nice pictures that you have seen. This is the MIRI instrument that was built by a US-European consortium, of which the Netherlands was a partner. And then there's also the NearSpec instrument that you see over here. So what makes it unique? Well, it's really, thanks to the big telescopes, thanks to improved technology, we are more than 100 to 1,000 times more sensitive than previous instruments. So there's really a huge discovery space. So web has been returning beautiful images. This is just a few here, beautiful galaxies that you see, star-forming galaxies. Actually, everything that is red is with our MIRI instrument, and that indicates actually the presence of warm dust, and that indicates the presence of star formation. Here is another one, the Cartwright galaxy, again, interacting galaxies that create sort of these fascinating regions where now active star formation is taking place. And much more, this is just a fairly recent set of beautiful images that have come again from galaxies, where we see both this star formation going on and also these fascinating structures of the clouds and the interstellar medium out of which new stars are forming. Closer to home, this is how JDBST and especially our MIRI instruments views the famous pillars of creation. This picture was released at Halloween a couple of years ago. It looks a little bit spooky, this particular image in the colors. But what you see here in the MIRI is actually, again, these little red dots. That is all new stars that are forming here inside these clouds. And this is probably one of the more famous images that came out, the first image release of JDBST. This is, again, the same Carina nebula that I was showing you before from Hubble, but now in the eyes of JDBST. And what you see here is this beautiful cloud with stars. Again, all of the red and dark yellow dots are young stars that are actually forming here inside this cloud. Now, I should say that because we cannot see the infrared radiation with our own eyes, what astronomers have to do, they actually have to give every filter a color that we can see with our own eyes. So blue is usually the shortest wavelength infrared radiation filter, and red is the longest wavelength infrared filter. And in that way, we make actually visible the radiation that our eyes cannot see. So there's no manipulation of the data. It's only how we display this in terms of colors. So here is actually where we see one young star actually with an outflow. It's trying to push away its surrounding here at the edge of this cloud. And here we see another young star where we see the result of it, a bow shock, actually plunging into this particular cloud. So lots of science happening there. Now, this is actually for one of our own JDBST program. It's a very young star. It's probably an analog of our own sun when it was only 10,000 years old. We cannot even see the young star itself yet. This is a PowerPoint dot. Everything is still completely obscured by the huge amounts of dust that are around it. Even JDBST cannot yet penetrate that. But what we do see is sort of these jets and outflows that are coming out of the young stars and that are trying to push away the surroundings and allow material to actually accrete onto the young star. And so this was also picked up by nature, and they changed the orientation a little bit and the colors, but they had a very appropriate title, actually, that a star is born. That is what you clearly see over here. Okay, so let's go back actually to astronomy and art. And this is actually an engraving that dates from 1798. And it shows not just our solar system, but this artist already actually speculated about other solar systems. You know, could it be similar or would it be different? More planets, fewer planets closer by, farther away? This is, of course, exactly what we're now finding in the study of exoplanets. There's this huge diversity, actually, of planetary systems. And so where does that come from? Well, it must originate in those disks, in those rotating disks of gas and dust. And so let's look a little bit about how we think that from these tiny little dust grains, we actually build these larger and larger planets. So we zoom in again, and we have our planet there that is creating this, maybe creating a cavity, but we also have these smaller dust grains that are infalling into the star, and they are actually coagulating and making larger and larger bodies. Sometimes they also bump off each other. But step by step, you actually go from tiny little sand grains to larger and larger bodies. And we now also know that these planetesimal, these planiform disks are very rich in chemistry. This is from a result from our group that was actually led to this particular movie there, where we saw various organic molecules actually in such a planet-forming disk. So in the simplest terms, we go from these tiny little dust grains to something that looks like Earth, or may not look like Earth, but there are various steps in between. And the key steps are actually making kilometer-sized bodies, what we call planetesimals. Those are actually the size of comets. So comets are really very important building blocks, because by that size, gravity starts to take over again, and you start to make planetary embryos, say moon-sized bodies, that then eventually can merge to make something that looks like Earth. So we are now actually in a very fortunate time where we can study sort of where we now have the techniques. This is completely new since 1985. Since 1980, in that period, we didn't know anything yet about these planet-forming disks. Now we have actually the techniques in order to study them. And with ALMA, we can study the outer parts. With JWST, we can actually look at the inner parts of these disks. And there's a huge synergy actually between these instruments. We can look at both the gas and we can look at the ices. And one important concept here is actually that of snow lines, which is the location where a molecule goes from the gas actually to the ice, as you see beautifully here in nature. And the importance of the ice line is that if you're close to the young star, it's warm. So our planetesimals will be just rock, like the asteroids in our own solar system. Whereas if you go further out, they will actually be cold. They will be ice-coated, just like the comets. And so every molecule has its own ice line. Water ice line is, say, over here. Carbon monoxide is much more volatile, and it would be over here. And astronomers have speculated already for a long time that the so-called water ice line would be a very favorable location to make giant planets, to make actually Jupiter-like planets over there. Well, that is a story is certainly has some validity, but now there's another story, namely that these ice dust grains can actually move in the disk, as we saw in that little movie. And when they cross the snow line, they actually will sublimate and they will put their material back into the gas phase. But there may also be dust traps. I mean, there may be like some of these structures that we saw in the ALMA images that can actually trap material at a larger distance and prevent it from actually going into the air. So we're now realizing that probably a lot of this variation that we see in exoplanets may be actually linked to what is happening in their planet-forming disks. Now with web, we can observe all of these components. We can observe the ice, we can observe the gas. This is just one example of a beautiful study by my colleague, Melissa McClure, of looking at a cloud, actually with JWST, and looking at the absorption on background stars and seeing their composition. And this is just one example of one of these fingerprints that we see with JWST, a hugely high quality spectrum, where we see here the background star, the continuum, and then all of these absorptions of the ices superposed in this water ice, CO2 ice, CO ice, and other ices. So we can now make an inventory actually of all of these ices. And we see not just simple molecules, but we can also find these more complex molecules that we were already hinting at. You see not just CH4 here, but you see also our ethanol again, and some of these other molecules that we can now see not only in the gas, but actually see them present in the ices. And this is very recent results that our group had with JWST, and which also led to a very nice press coverage by NASA, where it was picked up that apparently Webb now finds not just vinegar, but also margaritas in space, and also other molecules that you see over here. Good, but we go further. We find not only in the early stages of star formation, but also in these planet-forming disks. We find the various signatures of the molecules. This is just one example of water that is detected in a planet-forming disk in the region where terrestrial planets are forming. And again, this got a lot of attention because it was the first time that we actually saw this warm water here in such a planet-forming disk here close to the star, and showing that in spite of these dust traps, there is actually significant water coming into the region where new planets are being formed. But water is apparently not everywhere, even though it is certainly present in the outer parts of the disk. Whether or not it makes its way to the inner part of the disk, where these terrestrial planets are forming, that's a whole other question. And some of these very low mass stars that we are now having, these are exactly the type of stars that Professor Vardya was actually studying. These kinds of stars have disks that are actually full of hydrocarbons, almost no water, but lots of acetylene, even benzene is seen in these kinds of disks. And that's still a mystery as to why they are, but we have now found several of these disks. In fact, one of my PhD students jointly with Inga Kamp in Groningen is an Indian student from India, Aditya Adabavi, and he had a paper in Science just recently where he showed not just CH4, but also C2H4, ethane for the first time detected. Here you see various other molecules, like here's benzene again, also CO2 and several other diacetylene actually. This star is, the disk around this star is also full of these hydrocarbons. It's something that we don't understand yet as to why, especially these very low mass stars are so rich in hydrocarbons, but it may actually have implications for the kinds of planets that you will form around these very low mass stars compared with more massive stars. Okay, I want to end here actually, but leave you with the question as to whether these new worlds, these planets that are being made, whether they could be habitable. Then of course we need to look at the signatures of the exoplanets themselves, the mature exoplanets, not the young ones that we are looking at so far. And we need to look at possible biomarkers, like we have here, ozone, O2, etc. Not just one, it's probably a whole combination of molecules that we need to look at to decide whether or not some of these clouds are actually habitable and whether they could even be life on them. Some of that work is now being done by JWST. This is now a fingerprint, a spectrum of one of these exoplanets. And we see clearly water there, we see clearly CO2 there, but also surprises like SO2. So this is wonderful work by the team that's actually looked at that, the so-called ERS team that's built that. Also, other teams are looking at not just various water and CO2, but they're looking at clouds. We can now start to look at weather on exoplanets. Is it going to be cloudy in the morning or the afternoon? I think we will soon get some weather reports from some of the planets. In fact, we have already had one weather report of a sandstorm on an exoplanet's atmosphere. So this is the wonderful kind of work that is now being done also with JWST on these other planets. But eventually, we really want to go to the question is there actually life on the nearest planets? I don't know yet whether JWST will get there. Probably we need other future facilities in the coming years, like these giant telescopes that are being built at the moment on the ground, the extremely large telescope. And this is our nearest neighbor star, Proxima Centaurus. This is an artist impression of what sort of that planet could look like. And so that is, together with JWST, the ELTs, and maybe even other future missions, the big question is, can we then answer whether or not we are alone? So the whole question of the origin of life is just an endeavor that is science at large. It's not just astronomy. Many different disciplines come together, like chemistry, like physics, like geology, mathematics. Everything comes together to answer that particular question, as you see here in this nice little illustration. What I've talked to today is just the first step, whether or not we can make a habitable world. But my colleagues in chemistry are actually the ones that go this path, that then go from the very simplest periodic synthesis to making the first cells and to making then looking at the origin of life. So we all play our role in sort of this quest to answer the question as to are we alone? Okay, let me end actually with two of the very powerful images that astronomy gives us for society. The sunrise image that was taken. And that this one, the famous pale blue dots, that's Carl Sagan put towards our, that's us, that's our little, that's we, that's our home. So far away, picture taken from when Voyager was already beyond Saturn and looking back one more time and seeing that pale blue dot that was actually there. I'm a scientist that came from chemistry, and I now know that astronomy is an exceedingly exciting field to work in. It really provides inspiration. It's very exciting work. But most importantly, I think it also provides us with perspective, a little bit of a sense of vulnerability, modesty, and also tolerance. And I think these days, certainly with everything that is going on in this world, I think that's a very important message that we can have. Let us take well care of our planet, and let us realize that we are all world citizens under the same beautiful sky. I thank you very much.
Thank you, Erwine, for that enlightening and entertaining talk. We can have questions now. Can you guys use microphone? We can have questions. Please raise your hands, and people with microphones will come to you if you have questions.
A question from astronomy enthusiast, not the astrophysicist, learning or teaching. We hear a lot, read a lot about James Webb Telescope getting some images, some hard proofs of distant galaxies, stars. And when we read about them, we are surprised that when we talk of Big Bang, which is so many billions years away, then how this star could have been there, how this galaxy could have been there. Can you throw some more light, especially in your field or otherwise? Are we getting somewhere else than Big Bang?
So indeed, of course, Webb was designed to look very deep in the universe. It was designed to look for the first stars, basically, and the first galaxies, and it's getting close to the first few hundred million years after the Big Bang. And indeed, the surprise is that galaxies are already much more developed. Much more in their shape than we had expected before. Also, the elements, that's I think the more important part, is a lot of the elements are already there. We see neon at very large and oxygen at the very large redshift. So far, people have not yet found real evidence that it sort of breaks the known laws of physics. There have been claims in the popular press that it breaks the laws of physics, but the experts say no, it doesn't yet, but it definitely provides puzzles that they don't fully understand yet.
Other questions? Yeah.
Hi, thank you for the lecture. I found it really interesting. I was just wondering, how different is it to study astrophysics and astrochemistry now, whereas when you were studying astro?
Oh, that's a good question. What I think is that every topic actually that we study has become more specialized. So what you always still need your same background. So the background and the basics haven't changed. The laws of physics are there, and that's what you study in the first few years. But then, in terms of your specialization, then you go into sort of much deeper into a certain, maybe somewhat narrower topic than people did before. But you have the opportunity to work with fantastic new data that are present there. What I find as a chemist, when people come to me and they want to do astrochemistry, I find that it's actually much easier for a chemist to learn something about astronomy than for an astronomer to learn something about chemistry. So I actually encourage chemistry students to come to this field. Yeah.
Other questions? We had.
Yeah. Go ahead.
Yeah, there's a question.
Good evening, ma'am. Thank you for the lecture. I'm an undergrad student in physics in Mumbai. So my question is, what you showed just now was we are studying lower mass elements like carbon, oxygen, silicon. But is it possible to view higher mass elements around stars in the dust particles? Or is it just not worth it to study them for now? Because as a star ages, it goes on to give higher mass particles.
Yeah. So that's
feasible.
Yeah, that's sort of the creation of the elements. And yes, it's definitely worthwhile to find out how we make golds. That is important. That happens indeed in the death of massive stars, in supernova explosions, in the merging of neutron stars is where you make some of these higher mass elements. But they are in lower abundances, and generally we cannot detect their molecules. So I come from a chemistry perspective, so I want to see these elements as part of molecules. And so the heavier elements, it's much more difficult to see them as part of molecules. So that is why I talk primarily about the elements that are the key elements that make life.
There's a question at the back there. No? Okay. Out here.
Ma'am, in your concluding statement, you said that the study teaches us humility and tolerance. What do you make of Elon Musk's attempts to colonize space, and now that Donald Trump, supported by Musk, has been elected president? Do you think it's a bit preposterous of man to assume that he can colonize other planets? Or do you admire his aims and the objective of man to reach beyond Earth?
So I think that the quest of humans to always go beyond, the next step, explore space. I think that's what makes us human. We are explorers. So that is certainly true. Whether or not we want to do that exploration in human exploration, like going to Mars, or whether we do that robotically with our big telescopes and with our solar system missions that explore or that land a robot on a comet or something else. I think that's a whole other question. Certainly, my preference is for robotic exploration. That from a scientific perspective, I know there are certainly a fraction of humanity that is very excited about going into space, going back to the moon. I think we have to go back to the moon. I think that's certainly we can learn a lot there. The whole Mars is another story that is going to be far from simple to do. But just to make sure, even if we do all of that, there is no sort of planet B, planet B, where we as humanity could go in case something goes terribly wrong with our own planet. So I think that's the lesson we also have from astronomy. We better take well care of our own planet.
There's a question in the back. Yeah, go ahead.
Can more planets come?
More planets?
Okay.
Yeah.
She was listening to the bit you said about the clouds around the stars forming planets. So she wanted to know whether there are still clouds around the sun so that can there be more planets in the solar system?
Very good question. Yeah, very good. That's an intriguing question. How long can you continue to form planets around stars? I think our own sun is done. It's no longer. It still has the remnants of that disk around in which the planets formed. So there's no opportunity anymore for instance in our own solar system to make new planets, but other stars that are, on their way to becoming mature, they still have, enough material, even when they are becoming more mature to perhaps form another planet yet. Yeah, so yeah, it's a good question. As long as the material is there and it gets together, then it can make new planets. Yeah.
So we'll have the final question here. Yeah.
Hello, ma'am. Good evening. It was wonderful listening to you. And to my very raw mind, some things definitely confused me a little. And one of them was this thing only. You told us about this water being formed on the dust particles in the clouds, right? And it was a very nice demonstration that you showed us through the animation. But I failed to understand how exactly it happens as per like my raw mind thinks that, okay, there's vacuum and space and I don't find a particular catalyst that ran this whatever process you went. And then you followed this talk with the water reservoirs in perhaps the protoplanetary disk you were talking about. I'd like to know more.
Yeah. So the hard part is if you have a hydrogen atom and an oxygen atom, how do I bring them together to form a molecular bond? Here at the high pressures on Earth, it can happen. You need to this is very technical now, but you need to get rid of the energy that makes the bond. It's very hard actually to bring two atoms together to make a bond. And on Earth, actually what happens is you have molecular oxygen and molecular hydrogen, and they have a big bang and very violently you make water in that, but only a tiny, tiny little bit of water. The way you bring hydrogen and oxygen together is really put them on these tiny little dust grains where they can sort of meet and greet. Then that they can find each other and making this bond, and the extra energy then goes into the dust grains, and that stabilizes the molecule, and that's how you can actually make lots and lots and lots of water there. And that water can then actually find its way into these disks, and then also in these icy bodies like comets, and they and other icy bodies can then deliver this to young planets.
Thank you, ma'am.
Yeah.
There's a question on the YouTube.
Actually, not YouTube. So somebody has personally messaged me a question. He's a friend of mine from Nehru Planetarium. So he has actually sent me a research paper. Actually, it's a review article that that says that moons are planets. So on that particular review article, he's asking, Pluto cannot be removed as a planet since you have been the ex-president of IAU. So what is your decision on this?
Yes. So I think as scientists, we discover more and more objects in our solar system. We have the well-known planets, but then starting some 25 years ago, we started to discover these other objects that were actually as big as Pluto or sometimes even bigger, that were also there in our outer solar system. And that made us realize that, both asteroids, planets, moons, they all come in different sizes and have different characteristics also from how they are formed. And that's how sort of at least the IAU and its famous meeting in, in Prague in 1996, sort of adopted a new definition of the planets, which limited to the 8 bigger planets in our solar system and made Pluto actually one of the largest one actually of a new class of dwarf planets, as we call them. Of course, moons, all of these satellites, all of these planets have their own moons around them. In fact, they form very much like the planets form in a circumplanetary disk, is where you form these satellites, the moons. And they are, of course, also part of this whole collection of that. So in terms of their formation processes, they are not that different from how planets form, but they are circling a planet rather than that they are circling the sun. So I would say that we have a very rich solar system. We have planets, we have dwarf planets, we have moons, and we are still learning as to what is out there.
Hello. Yeah. Thank you. I hope this satisfies my friend.
I think Sujay, I think we should bring this session to a close.
Yeah.
I know there are no questions on that. So let's thank Professor Dishoeck again for this wonderful talk.
Thank you.
So please join us for tea and snacks at the cafeteria outside the auditorium. We can continue discussion with.
I also have a few little postcards from JWST, especially for the younger people in the audience. If you want to have one, please come up front here, and I can give them to you. Like that.